Let's look at icebox problem number 3 on page 8 of your homework packet. So we have the same equation we've been working with. Okay, I think the first time you were given, one time you were given just reactants with 0 products. One time you were given just products and 0 reactants. This time you have both reactants and products. Okay, by coincidence, this happens to be equal amounts of these things. But what do you do if you have equal amounts of things? Is it going to shift left? Is it going to shift right? To determine that, you need to find what we'll call is a Q value or reaction quotient value, and that's going to tell you which way you should manipulate this. So let's first find the equilibrium constant expression. We did this in the other two problems. It's products over reactants, and going back up here, I minus and BR2 are the products, and then IBR, 2 IBRs is the reactants. So taking that, we got I2 times BR2 over IBR squared, because there was a coefficient of 2 in that thing. Okay, so that's what we're going to be using right there. So we're going to use that. Now, what is the Q? A Q expression looks the same as the K expression. Should have clarified that as well. In fact, what is the Q expression? It is like an equilibrium constant expression, but it actually also applies when something's not in equilibrium, and it helps predict what you need to do to establish order. Which way is it going to shift to get into equilibrium? So it's products over reactants, doing the exponents the same way as the K value. But what we do is we plug in our initial values, which probably aren't in equilibrium, okay? And then we check that over. Well, it's 1 times 1 over 1 squared, it's 1. Now that value equaled, this 1 equals the K equilibrium constant, then it would be an equilibrium. But when Q is greater, it means we have too big of products for this equilibrium constant and too small reactants. So some of the products are going to move back toward reactants, or that'll be the net effect, and they'll go back and forth, but the net effect will be products to reactants. In other words, it will shift left in this case. So what's going to happen is if it shifts left or it's moving in this direction, how much is it going to shift? It's by an amount X. And remember, the IBR is going to be 2X because of the 2-to-1 ratio. But that does help us establish, if it's shifting left, that the I2 and the BR2 are going to become less. So we say minus X for those. And then this is going to be plus 2X because the reactant side is going to be gaining. Okay, and we have figured that out because Q was greater than the equilibrium constant. The Q is overvalued in the product side. It has to move back in the other direction. Now this just becomes like really any of our other problems. I look at this and, oh, well, I started with this. It's going to be 1.0 plus 2x. This is going to be 1.0 minus x, 1.0 minus x. So we got a lot of things to deal with, not a particular x value. But again, if we plug this back into the equilibrium constant expression, which is the same as this for the Q value, we can look down here and, oops, kind of lost that a minute. Okay, we can take, let's see, this is K value, okay, and then we have the 1.0 minus x times 1.0 minus x, one for I2, one for BR2, or otherwise just squaring it, and the 1.0 plus 2x comes from here. I take the square root of each side, so I get this. I solve for the square root, I get this. I move this term over here, and I end up here, and ultimately, I keep going with the algebra and then solve and get 0.77. Okay, what is a 0.77? That is the value of x. Okay, notice none of these concentrations are x like in the other two problems. So I'd have to go, 1.00 or 1.0 minus 0.77 is 0.23 for this. It's 0.23 for this. And then I do the 1 plus 2 times 0.77 to get the 2.54 here. So that's what I do to figure out these values, and these would be my concentrations that I need. I should double check to make sure this is correct. I'll take what the I2, which is 0.23, the BR2, which is 0.23, divided by 2.54 squared. I get 8.2 times 10 to the negative third. Okay, I think I'm supposed to get 8.5 times 10 to the negative third. That's okay. It seems like it's off a little bit, but that's pretty typical when you're rounding things just to two figures. So that last digit is going to definitely do some floating. So this looks like it verifies that. Does it make sense if we started with the same amount of each that we have more reactants, less products? Yes, because the equilibrium, K equilibrium, is quite a bit less than one, not ridiculously so, but quite a bit less than one. So these numbers are quite a bit bigger than this. Certainly these are not negligible numbers. They're definitely significant, but we see a pretty good distinction right there. All right, that's just another example of an I-square problem or icebox problem with a kind of a perfect squares that we have for this. Thank you.